Hi everyone, and welcome to our this video lecture while I'm out of town. We're going to just cover one specific concept, which is how the energy levels of atoms change when we start adding multiple electrons and going beyond the really simple system of helium to things that become more complicated. So we already said that we were going to approximate our wave function as Slater determinants. Remember, the Slater determinant is a mathematical device which allows us to make an antisymmetric wave function of single electron orbitals. So if we go across the Slater determinant, we're going to have different, each column will have a different electron in it. As we go down the Slater determinant, the different rows will have a different orbital. Okay? We can calculate the average energy using the Hartree-Fock method. When we find the average energy, we're going to have to solve to figure out what those orbitals are, and we're going to get out orbital energies. That's great. We can add those up to get the total energy of our atom. But there's something a little bit better, which is called Koopmans' theorem, which says that the orbital energy, epsilon sub I, is the same as the ionization energy of the ith orbital. Or in other words, how much energy it takes to remove the ith electron from the atom. And this gives us an experimental observable that we can compare to. We can use photoemission to study when we can get an electron off of the atom. And in particular, we're going to look at the easiest electron to remove, or the onset, as soon as we start getting electrons coming off. And that's called the ionization potential. And the ionization potential is defined as the lowest amount of energy required to remove one electron from the ground state of an atom or molecule. And at this point, we can ask, what should we expect to see here? And in particular, we're going to focus on the second row of atoms, so lithium through neon, because we're going to be putting multiple electrons into 2s and 2p orbitals. Now, in the hydrogen atom, all of those orbitals were degenerate. And so if they were still degenerate, then you would expect that the ionization potential wouldn't change. As we went, say carbon to nitrogen, they're all putting electrons in the 2p, they're all putting electrons in the 2p orbitals. So does the energy required to remove an electron change? And it turns out that there's significant differences. So let's go take a look at a graph of the ionization energy as a function of atomic number, or Z. And the ionization potential, here we see hydrogen and helium over on the left-hand side. And then there's a big drop down ionization potential. It becomes much easier to remove an electron. And as we go across the periodic table, it gets more difficult, except you can see there's a little bit of a blip between going from beryllium to boron. Right? And that's interesting. But as we go across, we see that we get this shell-like structure. So we have n equals 1 to 2 when we change from helium to lithium. Our principal quantum number, 2s and 2p, is going to 3s and 3p once we get past neon. And then once we get to potassium, we're going from the n equals 3 to the n equals 4 level. So we have these little blocks or shells of energy levels where we have big changes after each one. And that's the exact same picture that you would get from what you studied in general chemistry. The energy shell-like model for the atoms. Okay? And so let's get back to this question of why is it multi-electron system? Why are the orbitals different? Why is a 2p orbital different in energy than a 2s orbital? And the answer is the electron-electron repulsion. And remember, for the 2s orbital, that on average, the electrons were further away from the nucleus, but there was that little blip in the radial portion of the wave function where the electron was close to the nucleus. When we throw in electron-electron repulsion, that makes the 2s orbitals lower in energy than the 2p orbitals. And this leads to the familiar shell splitting that you've seen since general chemistry. The 1s orbital is lower than a 2s orbital. A 2s orbital is lower than a 2p. A 3s is lower than a 3p, which is lower than a 4s, which is lower than a 3d. It's just the same energy level ordering. And we're going to call each of these a shell. And a shell is going to be a set of orbitals with the same value of total orbital angular momentum, or L, or quantum number, including spin. So there's 2 different states for an s orbital, 6 different states for a p orbital. That's L equals -1, 0, and 1. Sorry, L equaled 1, m sub z equal to -1, 0, and 1, and the 2 different spin states, alpha and beta. So similarly, we have 10 d states and 14 s states. Okay. And the primary thing to take away is that the energy degeneracy associated with a hydrogen atom is broken by the electron-electron repulsion terms. Okay. So now we can figure out which energy shells are going to have the lowest energy. We can put electrons into each shell, filling up those states. This is called the Aufbau principle, where when we think about our atomic structure, we populate the energy levels of atoms with individual electrons corresponding to the energy level of each subshell, and we fill each shell before adding electrons to the next shell, and this will give us the ground state energy of the system. And remember, each shell corresponds to an orbital angular momentum, and we're going to use the following set of symbols to designate our configuration. We're going to have a number, n, which will represent the principal quantum number, a letter, L, which will represent the orbital angular momentum of that shell. So 0 orbital angular momentum is S, orbital 1 is going to be a P, 2 is a D, 3 is an F, etc. And the number we're going to put as a superscript as how many electrons are going into that shell. Right, so let's give the example for the first 10 elements. Hydrogen would be a 1s1, helium would be a 1s2, lithium would be a 1s2, 2s1, right? So we got to go to the next quantum number, next principal quantum number. Beryllium, we're going to fill up the 2s orbitals. Boron, we're going to have 1s filled. The 2s orbitals are going to be filled with 2 electrons each. And then we start putting electrons into the p orbitals. And we keep putting electrons into the p orbitals until we get up to neon, which has the configuration 1s2, 2s2, 2p6. Okay? So this is sort of where you would have left things at general chemistry. We're going to put electrons into these different configurations for the different atoms. But it turns out that that's a bit ambiguous. Oops, I think we said boron and this should be carbon. So let's take a look at the configuration for the carbon atom, which is 1s2, 2s2, 2p2. And let's ask a simple question. Should those 2p electrons go into the same p orbital, or should they go into different ones, or does it make any difference at all? Well, it turns out that it does make a difference, and the energy is going to be lowest if they go into 2 different orbitals. And the reason comes back to thinking about the electron-electron repulsion term. Each of the 3 p orbitals are spatially orthogonal to each other. So if we place 2 electrons into the same p orbital, they're going to be nearby each other, and that will increase the electron-electron repulsion term. If we put them into different p orbitals, then they're not as close together, and that minimizes the electron-electron repulsion and gives an overall lower energy. Okay? And so electrons want to spread out, so occupying each orbital singly in a subshell will be lower energy than putting 2 electrons into an individual orbital. And there's no way that you can get that information just by looking at the configuration. The configuration is ambiguous. It actually gets a little bit worse than that. Not only does the electron-electron repulsion tend to want to make the electrons spread out into different states within a given shell, we actually have to think about magnetic effects. So when we give the atomic Hamiltonian, we didn't include magnetic effects at all. But if we're thinking about smaller changes in energy, they actually become important. So remember that magnetic charges, moving charges, create magnetic fields. And it turns out that an electron moving with angular momentum will create a magnetic moment. And another electron that's nearby will actually want to line its magnetic moment up with the magnetic moment of the other electron. And this is going to tend to make electrons want to have the same magnetic moment, which will depend on their angular momentum. And it doesn't matter whether that angular momentum is caused by the spin or the orbital angular momentum. So let's see. This leads to 2 separate new interactions. The first is spin-spin interaction. And that is if 2 electrons occupy spatially degenerate orbitals, then the energy of the system is lowest if the spins all point in the same direction. That will cause their magnetic moments to point in the same direction, which will be lower energy. So the energy of having two alpha states versus an alpha and a beta state, it's going to be lower when we have the two alpha. And that will end up having the same energy as if we have two beta. Now there's a separate interaction. So the spin-spin interaction requires multiple electrons. There's a separate interaction, which is a little bit weaker, which is called spin-orbit interaction. Okay, and that's going to want to make the angular momentum of the spin of an orbital, a spin of an electron, point in the same direction as the orbital angular momentum. So it's going to be lowest in energy when the m sub z has the same sign as the spin of the electron. Okay? Now, obviously, m sub z is 0 for an s orbital, so this only applies for p, d, f, g, and h orbitals. Okay? But this means that thinking about what the lowest energy state becomes significantly more complex. We can't get that information from the configurations, and so we're going to have a more detailed description of what states our electrons are going to be in by using something called a term symbol. Okay, so we're going to label a state with a term symbol that shows its angular momentum. All states from the same configuration and the same term symbol are going to be degenerate. All right? And so knowing what the term symbol is, in addition to the electron configuration, will give us a much more precise handle on what the electrons in our system are doing. Okay. So remember, each of the orbitals that we talked about have a definite orbital angular momentum quantum number. They have a definite L. Okay? Now, they may or may not have a definite m sub z, or an orbital angular momentum Lz, right? Remember, we could have a px, a py, and a pz. And of those, only pz has a well-defined orbital momentum projection onto the z-axis. But they all have orbital angular momentum L equal to 1. And each of those orbitals, those phi sub i's, are also going to have a well-defined total spin quantum number, which is 1/2, and an m sub s, a spin quantum number corresponding to alpha or beta, which will be h bar over 2 or minus h bar over 2 angular momentum projected onto the z-axis. If we add all of these orbital angular momentum up, we should be able to determine the spin, the orbital angular momentum, and the total angular momentum. Alright, so let's take a look at this term symbol, 2s plus 1 Lj. The 2s plus 1 is the spin multiplicity. In other words, it's how many states have everything else the same, it's how many states have the same total spin, right? So when people talk about a singlet or a triplet or a doublet, right, this is what they're referring to. It's how many states have the same total spin, and in those states that may be projected differently onto the z-axis, but how many states have the total spin quantum number. The letter L, the capital letter L, will tell us the total orbital angular momentum quantum number. And so, just like the little l's, this is going to be a S, P, D, F, or G, but we're going to make it capital so that it's obvious that it's representing the total orbital angular momentum of all of the electrons in the atom. And then we're going to have a separate quantum number J. And J is going to be the addition of spin and orbital angular momentum. And so, finally, our term symbols are going to look like what's down here in the bottom of this slide. A superscript number 1, a letter S, P, D, F, or G, and then a final number down here at the bottom, which will be the spin, which will be our J value. Okay? So, this actually gets to be a little bit complex, and so we're going to work through this on a worksheet on Wednesday. And the reason is that orbital angular momentum and spin angular momentum, these are vector quantities. And so they add like vectors. If we just have two orbital angular momentum, electrons in two different orbital angular momentums, they can point in the same direction, or they can point in opposite directions, right? And remember, in quantum mechanics, there's some uncertainty when we deal with orbital angular momentum or angular momentum in general, right? We can only know two different quantities. First, we can know the magnitude of the angular momentum, and we can know how much of it projects onto the z direction. Okay, so if we're going to do an example here where we have two electrons in two different states, right? When we want to get our total angular momentum L, we need to add these two vectors together. And the magnitude of that new vector is not going to be the simple sum of the length of L1 and L2. And so they don't add together like scalars. The component along the z direction, however, that does add like a simple scalar. Right? So if we have L1 sub z plus L2 sub z, we'll get the total amount projected on the z-axis. If we add all of the angular momentum quantum number, or all of the orbital angular momentum projected onto the z-axis together, we'll get capital M sub z. And this is pretty simple to calculate. Once we know capital M sub z for a given state, we know that gives us some idea of what L could be. Not what it is, but what it could be. Remember, when we've been assigning M sub little m for angular momentum, we've been saying that it can take on a range of numbers, right? It can go from minus L to minus L plus 1 to minus L plus 2, all the way up to L. Well, now we're going to end up working in reverse. We're going to be able to figure out what the angular momentum projected onto the z-axis is, m sub z, and then we're going to know that the value of L, capital L, has to be greater than or equal to our value for m sub z. Right? There are going to be a number of different states that can correspond to. Similarly, we're going to do the same thing with spin. So each electron is going to carry around a spin of 1/2. That's the magnitude. We're going to associate the spin angular momentum, and that can project it either onto the z-axis or onto minus the z-axis. So we get our two alpha and beta states. Again, the total spin is going to add like a vector, but the component onto the z-axis, the alphas and the betas, add like simple scalars. So we can add up the total spin angular momentum projected onto the z-axis to get capital M sub s. And then once we know that M sub s, we can have a guess, or we can determine what the total possible values of capital S are, because they have to be greater than or equal to the absolute value of M sub s. Once we have all of that information, we can determine our term symbol, and we'll work through how to do that. And then we can determine which term symbol is going to be the lowest energy by using Hund's rules. All right, thanks so much. We'll talk about this on Wednesday.